Hello, my name is Rahel Salehi and I'm coming from Helmholtz Munich. Today I'm talking about unsupervised cross-domain feature extraction for single white blood cells. Hematopoietic malignancies such as leukemia are among the deadliest diseases. Computer-aided diagnosis systems are becoming an essential element for proper diagnosis. Finding the hallmark cells of these diseases in patient samples is a tedious task for cytologists. Computer-aided diagnosis systems help cytologists to speed up the process and get accurate performance. When computer-aided diagnosis systems are trained on data from a given center and are tested on the same cohort, the performance is acceptable. While if the data is coming from another center, the accuracy isn't good. And this challenge is called domain shift. Here, it is an example of images. We want to focus on white blood cells and remove the artifacts surrounding them in each image. There are some challenges in annotation of white blood cells data. For instance, there isn't a standardized definition of classes, or to annotate the white blood cells, we need to train human experts who are expensive and scarce. Additionally, we have to annotate the new dataset every time. We have 3 different datasets. MICCAI, it has 18,000 white blood cells in 15 different classes. INT20, it is around 42,000 images in 18 different classes, and Acevedo, which is over 17,000 images in 8 classes. The defined model starts with a MICCAI CNN. It is trained on only 1,500 images for instance segmentation. To annotate a dataset from MICCAI CNN, there is no need for any expertise and information about the cells. MICCAI CNN not only detects the single cell, but also thanks to region of interest align function, we can have the corresponding feature vectors, which will be used in the next step. But these feature vectors are sparse and we need to minimize them further to have better meaningful features. So we propose a 2-stage autoencoder which consists of feature encoder and decoder and an image decoder. MICCAI CNN helps to eliminate artifacts surrounding the white blood cells, so autoencoder uses features that are focused only on the target cells. There are 2 different loss functions, which are MSE loss for calculating the similarity between reconstructed features and extracted features, and SSIM loss function that calculates the structural similarity between the original images and reconstructed images. Because of domain shift, the distributions in the latency space are far from each other. To bring the distribution close to each other, we use group normalization after each layer of encoder and define a maximum mean discrepancy loss, such that the distance between means of the distribution is minimizing with MSE loss, and symmetric KL divergence works on the covariance matrices to maximize the similarity. After applying these 2 techniques, the distributions are getting close to each other. Since we have 3 different datasets, we categorize all classes into 13 commonly defined classes, and then we apply a random forest classifier model to classify the extracted features. This is our way to evaluate usefulness of the features we extract with our method and observe the severity of domain shift impact. Random forest is simple and a standard classification method. We divided the dataset into train and test set of 80% and 20% respectively. Every time we train only one of the datasets and test on the rest. We repeated this experiment on the other dataset as well. As a baseline, we compare our model with MICCAI approach. We trained only on MICCAI 19 dataset and got 96% of accuracy. We tested his model on the other datasets and got only 29% for INT20 and 8% for Acevedo 20. Since he used a ResNext network, we trained a similar ResNext on INT20 and got these results and repeated the experiment on Acevedo 20. So you can see our model outperformed the baseline for the state of the art in terms of cross-domain accuracy. For conclusion, our proposed model eliminates artifacts surrounding the white blood cells with MICCAI CNN. To have meaningful features, we use an autoencoder, and to solve the domain shift challenge, we use group normalization and maximum mean discrepancy to align the latency space representations. For the future, we are planning to extend the method and address some of its shortcomings. So far, the domain shift is only assumed to be present between different datasets, so handling the domain shift within each dataset would be desirable. Applying this feature extraction method on some diagnosis scenarios would better exhibit the capabilities of it. And finally, trying different methods of domain adaptation are just some of the exciting direction to explore in future. I would like to thank you for your attention.